Hey everyone, and welcome. Today we're doing a deep dive into a really powerful statistical technique called two-stage cluster sampling. So picture this. You've got a population that's naturally grouped into clusters, right? But measuring every single item in a cluster you select is either way too expensive, takes forever, or it's just, well, redundant. We're going to see how sampling in two stages gives us a much more flexible and, honestly, a more efficient way to get the answers we need.
Okay, so here's what we've got on tap. First, we'll tackle the why. What problem does two-stage sampling actually solve? Then we're going to get into the nuts and bolts, looking at two different ways to estimate our population values, the unbiased estimator and the ratio estimator. Then we'll have a little fun with an estimator showdown involving some, let's say, biologically unique puppies. And finally, we'll bring it all home by applying these concepts to a real-world study on coot eggs. Let's jump in.
All right, first up, why bother with a second stage of sampling? Well, it all comes down to the limits of its simpler cousin, one-stage cluster sampling, where you pick some clusters and then you have to measure everything inside them.
Yeah, just think about what this slide's asking for a second. Imagine you're studying classrooms. If the students in any given class are all pretty similar, they've got the same teacher, same books, same lessons, once you've tested a few of them, testing the rest probably won't tell you much new. You're just confirming what you already suspect. And in that scenario, one-stage cluster sampling is just not efficient. You're basically burning time and money to measure redundant information.
So the fix is actually pretty elegant. We break the process into two stages. First, just like we did before, we take a simple random sample of our clusters. We call these our primary sampling units, or PSUs. But then, and this is the game changer, we don't measure everything inside. Nope. Instead, for each cluster we picked, we take another simple random sample, but this time of the elements inside that cluster. And those are our secondary sampling units, or SSUs. So it's a sample of clusters, then a sample within those clusters. Simple as that.
Okay, so we've got the how. Now let's get into the math and talk about how we actually estimate things like the population total or the mean. Our first tool for the job is called the unbiased estimator, and we're going to build its formulas from the ground up.
Right, so first big question, how do we estimate the total? The challenge is that we didn't measure every single element, so we don't actually know the true total for the clusters we picked. We have to estimate it. The logic is pretty simple. You take the average value from your little subsample, that's your y bar I, and you just multiply it by the total number of elements you know are in that cluster, mi. And boom, that gives you t hat I, our best guess for that one cluster's total. Once you've done that for every cluster in your sample, you just add them all up and then scale that number by n over n to blow it up to the full population size. And that final number, that's our unbiased estimate of the population total, t hat unb.
There's another way to look at this, and honestly it's how most software thinks about it, through sampling weights. The weight for any one element is just the inverse of its probability of being picked. And that probability has two parts, right? First, the chance its whole cluster was chosen, which is little n over big N. And second, the chance it was chosen from within its cluster, which is little mi over big Mi. You multiply those two, you get the total probability. The weight Wij is just 1 over that. Then to get the total estimate, you just sum up the value of every element you sampled multiplied by its weight. It's a different path, but it gets you to the exact same place.
Okay, deep breath. This formula looks like a monster, I know, but it's actually got a really neat logic to it. That first chunk should look kind of familiar. It's basically the variance from a one-stage cluster sample. It captures the variability between the clusters. But that second term, that's the new part. That's the price we pay for subsampling. It represents the variability within the clusters. So think of it this way. Our estimate now has two sources of randomness. First, do we get lucky and pick clusters with high values, or unlucky and pick ones with low values? That's the between cluster variance. And second, within those clusters, do we get lucky and pick high-value elements, or unlucky and pick low ones? That's the within cluster variance.
So to actually use this thing, we need to estimate the variance from our sample data. It's pretty straightforward, actually. We just swap out the unknown population variances with their estimates from our sample. We use S squared I, that's the sample variance from inside each cluster, to estimate the within cluster part, and we use S squared T, which is the sample variance of our estimated cluster totals, to get at that between cluster part. You're basically just plugging in the numbers you can actually calculate from the data you've got.
But, and this is a big but, this unbiased estimator has a major weakness, a real Achilles heel. That S squared T term, the one capturing the variance between our estimated cluster totals, it is super sensitive to how different the cluster sizes are.
If some of your clusters are huge and others are tiny, your estimated totals, your t-hat i's, are going to be all over the place just because of the size difference. This can make that s squared t term explode, giving you a massive variance and a really, really imprecise estimate.
And that problem, that exploding variance, leads us straight to our hero of the day for situations like this. It's an approach that's way more stable when clusters aren't all the same size. Let's meet the ratio estimator.
Now this is where things get really smart. The ratio estimator doesn't just estimate the grand total and divide by a known population size. Instead, it computes a ratio using only the information from the sample it actually drew. To get the mean, it sums up the estimated totals of the clusters you picked, and then it divides that by the sum of the sizes of those same clusters. By putting a random variable in both the top and the bottom of the fraction, it cancels out those wild swings from cluster size. It's an incredibly clever way to stabilize the estimate.
And here's a little secret from the real world of data analysis. Those full variance formulas are a lot. But in many, many real-world cases, that first term, the between cluster variance, is just so much bigger than the second one that it does all the heavy lifting. Because of that, most survey software actually uses a simplified variance formula, sometimes called a width replacement estimator. It focuses only on the variability between the clusters. It's an approximation, sure, but it's usually a darn good one.
All right, enough with the abstract formulas. Let's make this real. We're going to have a little showdown, a head-to-head competition, to see just how dramatically different these two estimators can be when your cluster sizes are all over the map.
So imagine this little town. It's got 2 puppy homes. First, you have the Puppy Palace, a big place with 30 puppies. Then there's Dog's Life, a much smaller rescue with just 10 puppies. Here's our plan. We're going to randomly pick one of these 2 homes. Then, from whichever home we pick, we'll randomly sample 2 puppies and count their legs. And just to keep it simple, we'll assume every single puppy has the normal 4 legs.
All right, let's run the numbers with our unbiased estimator. What happens? Well, if we pick Puppy Palace, our 2-puppy sample has an average of 4 legs. So the estimated total for that home is 30 puppies times 4 legs each, 120 legs. To get the population total, we scale it up by 2/1, so we estimate 240 legs in the whole town. Now, to get the mean, we divide by the 40 total puppies, and we get 6 legs per puppy. Okay. What if we picked Dog's Life? The estimated home total is 10 times 4, which is 40. The population total estimate is 2 times 40, which is 80. And the mean is 80 divided by 40, or 2 legs per puppy. I mean, come on, our estimates are either 50% too high or 50% too low. That is just all over the place.
But now watch what happens with the ratio estimator. This is like magic. If we pick Puppy Palace, the formula is our estimated total from the sample, 120, divided by the total size of that cluster, 30. And that gives us 4 legs. Perfect. What if we pick Dog's Life? Well, it's the estimated total of 40 divided by the cluster size of 10, which is also 4 legs. It gets the right answer every single time, no matter which cluster we draw, because it automatically corrects for the fact that Puppy Palace is 3 times bigger.
This quote from our source text just nails it. The unbiased estimator is, technically, correct on average. If we did this 1,000,000 times, the average of all our wacky 6-leg and 2-leg estimates would eventually be 4. But for any one sample you take, it can be wildly wrong. This is a huge lesson in survey design. Unbiased does not always mean good. Sometimes an estimator with a tiny bit of bias, but much, much lower variance, is way more useful in practice.
Okay, puppies are fun, but let's see how this works in a real scientific study. We're going to check out some data from research on the egg volume of the American coot. Here, the clusters, our PSUs, are clutches of eggs, which is just the scientific term for a bird's nest. So the researchers sampled a bunch of nests, and then they subsampled a few eggs from within each of those nests. So here's the rundown of what the researchers found. They sampled n equals 184 clutches. Using that smarter ratio estimator, the estimated mean egg volume, y bar hat r, came out to 2.49. The average clutch size in their sample, m bar, was about 9.5. And that last piece we need for the variance, s squared r, is the variance of the residuals. A residual is just the prediction error for each clutch. It's how far off that clutch's total volume was from what you'd guess based just on its size. Here it was 62.51. Okay, time to crunch the numbers. We're going to use that simplified width replacement formula we talked about, the one that software often uses. The formula is basically that s squared r divided by n times m bar squared. So we plug in our numbers, 62.51 divided by the quantity 184 times 9.554 squared,
and that gives us an estimated variance of 0.0037. If we take the square root of that to get our standard error, we're looking at about 0.061.
So now we have all the pieces to make our final conclusion. Our best single guess for the mean egg volume is 2.49. To build our 95% confidence interval, we use a t-distribution. Now, the degrees of freedom here is based on the number of clusters, not the number of eggs. So it's 184 minus 1, or 183, and that gives us a confidence interval from 2.37 up to 2.61. What this means is we're 95% confident that the true average egg volume for all coot eggs out there is somewhere in that range.
Now, when you actually go to do this yourself in R or some other software, there are a few things you have to get right. One, you must tell the software what your cluster ID variable is. That's how it knows how to calculate the standard errors correctly. Two, you've got to provide those sampling weights. Three, remember, the degrees of freedom is based on your number of clusters, not your total sample size. And four, it's often a good idea to just skip the finite population correction, the FPC. This gives you a slightly more conservative, meaning larger, standard error, which is usually a safer bet.
I don't want to leave you with this last thought, because it's probably the most important takeaway from this whole thing. People can get really worked up about little details like the finite population correction. But the biggest mistake you can possibly make is to ignore the clustering in your data altogether. If you analyze this coot egg data like it was just a simple random sample of eggs, your standard errors will be dead wrong, probably way too small, and your conclusions could be completely bogus. Getting the cluster design right is everything. Everything else is a distant second. All right, that's a wrap on our deep dive. Thanks for tuning in.